Okay, so we're pretty much finishing out the course and we're going through, we have quite a bit, unfortunately, to get through. So today we're going to look at finishing up with logarithms and exponentials and looking at some applications with those. Then the plan is to look maybe at some variation problems and how to find the equation of a circle and graph a circle. So let's go into the application piece. And as we're going through problems, I'm just going to bring in maybe formulas that you should know. Actually, before I do that, I will give you a couple equations. So let's look at the formula for an exponential growth.
And we said this was 12.9?
So these are, I don't have the section number. I believe this is 12.8. I don't think there's a 12.9 in our book.
Oh,
and I'm starting not to put in section numbers just in case I use these videos in the future. And I have a different book and they don't match up. So that's why I didn't type that in. But exponential growth, and this is back in that section we skipped on applications of exponentials. But I wanted us to go through and look at logarithms because that helps us solve exponential equations. And it pretty much ties in with 12.8. So exponential growth, the formula for that is, let's say, y is equal to a times b raised to the x power, where b is greater than 0. I'm sorry, b is greater than 1. An exponential decay we have y is equal to a times b raised to the x power, where b is between 0 and 1. X is equal to time, so our variable, and the exponent. The variable a in front of the exponential piece, b to the x power, a is equal to the initial amount when time is 0. And then y is equal to the amount after x time. So really, your value of b is equal to 1 plus r, where r is equal to the percent and decimal. Form. For growth rate. This is for a growth rate. So if you had a rate that was growing maybe 25%, something was growing 25% every day, then we would have 1 plus 0.25, r would be 0.25, which makes sense. You're looking at something growing over 100% a day, and that's where the 1 is there. If it's a decay though, then it's less than 100% that you're getting back of the amount before. And so decay, we're going to have 1 minus r. Again, r is in decimal form. Okay, so going to an example, we're given the following. So a substance decays 22% each day. After 7 days, there are 9 milligrams of a substance remaining. How many milligrams were there initially? It might be faster if I type this, so let's try that. Let's see if you can read it. So a substance decays at a rate of 22% each day. After 7 days, there are 9 milligrams of the substance remaining. How many milligrams were there initially? So we need to set up our equation. We don't know what the initial amount is. We don't know back here in our equation what that A value is, but we have information about the growth rate. We have information about number of days and an amount that is given for that day. So let's start setting up the equation. So we have y is equal to some initial amount A, which we don't know, times, so this is telling me it's decaying, and so I'm going to do the 1 minus. So it's 1 minus the rate that it's decaying in decimal form. And so 22%, we're going to have as 0.22 to the x power. Okay, so from there, we need to figure out what A is. And so they give us enough information so that we can do that. And so they basically give us a point. So they say after 7 days, so this is the X value, X was time, there is an amount of 9 milligrams of the substance left. So this is our Y value when X equals 7. So if we go back into our equation and we plug in those values for Y and X, we'll be left with an equation just with A, and we can solve for that. And so we have Y is 7 is equal to A, which we're trying to solve for, all times 1 minus 0.22. So if you do that, you're going to get back 0.88. Oops. And I'm sorry, it was 9 milligrams. Y is equal to 9, not 7. So this should have been 9 equals. Okay. Raised to the X, and X in our case is the 7. Okay, so basically I just need my calculator. I need to get A by itself. I can divide both sides by 0.88 raised to the 7th power to get A by itself. And so A is equal to 0.88. I have to first raise that to the 7th power. Oops, I'm sorry. A is equal to 9 divided by 0.88 raised to the 7th power. So 9 divided by 0.88 raised to the 7th. A is equal to approximately 22 milligrams. Okay, so originally the substance had 22 milligrams, or there was 22 milligrams of the substance, and after 7 days, there was only 7 milligrams left. Let's put part B on this. So We just answered, this was 22 milligrams initially. So what if it asked, so what is the formula for the amount of substance after X days? Okay, so to figure that out, well, we basically have everything. We know that Y is equal to the amount of the substance. So Y equals A. Well, we just figured out what A is. A was 22 milligrams. So this is 22 milligrams all times 1 minus the growth rate, which was 22%. So this gave us 0.88, all raised to the X power. So now we can answer anything about this substance. So we could figure out how much substance is left after X number of days. So if we wanted to figure out what it was after 10 days, we would plug in 10 for X and plug that in the calculator. But what if we wanted to figure out how long will it take the substance to reach 2 milligrams? Okay, so we actually know what Y is. This is our Y value. So we have, and we're using our equation above. So we're looking at when is Y 2? So 2 is equal to 22, 0.88 raised to the X power. Okay, so this is an exponential equation. And so we need to solve for X. So we need to isolate that exponential piece. We want that 0.88 raised to that power by itself. And so first of all, we don't want that 22 in front of that parentheses. And so we can get that by itself by dividing both sides by the 22. 2 over 22 reduces to 1/11 is equal to my exponential piece, 0.88, all raised to the X power. Okay, so there were a couple ways that we just learned how to solve for exponentials if we could not manipulate the bases to be the same. And I can't manipulate those bases to be the same. And so that's where we use properties of logs to help us get that exponent out of, that variable out of it as an exponent and in front. So we want to take the log of both sides. So use logs to bring the exponent down. So we can take the natural log of both sides, or we can take the log of both sides. And we usually choose one of those because that's what our calculators do. And so if we took the natural log of the left-hand side, whatever we do to one side of our equation, we got to do to the other. So this is equal to the natural log of this 0.88 raised to the X power. So the whole point of that was so that we could bring our exponent down in front. And so now we have the natural log of 1/11 is equal to X times the natural log of 0.88. So we can get x by itself. Natural log of a number is just a number itself. It's whatever exponent you're raising e to get back 0.88. It's just a ugly way to write it. So we're just dividing both sides by that constant, natural log of 0.88. And so we get x is equal to the natural log of 1/11 divided by the natural log of 0.88. Okay, so I want to plug that in my calculator. So after you put in 1 divided 11 after the natural log, close that parentheses, divide by the natural log of 0.88. So this gives me about 18.7 or 18.8. Okay, so we were talking about time. And if you look back in the problem, the time that it was talking about was in terms of days. So it will take approximately 18.8 days of a substance that started at 22 milligrams to go down to 2 milligrams. Okay, so this was where I wanted us to have the tools to be able to solve for variables in the exponent. And now we can do that with knowing how to use logarithms. Okay, so let's look at another example. And I think I'm going to try typing it again. Okay, so we have Sam. He opened a bank account with an interest rate I can't spell. 4.8%. That compounded annually. He invested, let's say, $3,750 in the account in 2000. Oops. But had to make a withdrawal from his account in 2007 in the amount of $1,250. Fortunately, this was with no penalty. So how much is in the account now? $2,020. Oops. Okay, so we got money and an account. And so it's increasing 4.8% compounded annually. So let me just give you a formula real quick. So if we have A is equal to P all times 1 plus R over N raised to the NT. Okay, so A is equal to the amount after T years. P is equal to the amount invested. N is equal to the number of times compounded a year. And R is equal to the interest rate in decimal form. Okay, so we have a couple of things going on here. We have to take in consideration that in 2007, they withdrew some money. And so they're not gonna be making money off of what they withdrew. So let's first figure out how much money was in the account in 2007. Or figure out how much is in the account after he withdrew. $1,250. Okay, so the amount, this would equal to how much he invested. So let's see. He invested $3,750. All times 1 plus the interest rate. So the interest rate here is 4.8%. So we're going to put this as 0. It has to be in decimal form. So move that decimal over 2 places to the left. So 0.048. It tells me it's compounded 1 time or annually. So that's just 1 times a year. Where did it say that? And we have to figure out how many years it was in the account. Well, from 2000 to 2007, that was in the invested for 7 years. Okay, so that's how much money he's made in 7 years off of the $3,750 invested at 4.8%. But we just said that he is taking some money out, that $1,250. Okay, so we just need to figure out what we have. So we have A is equal to order of operations. We need to first work what's inside our parentheses before we raise it to a power and before we multiply. And so here we have 1.048. We're going to raise that to the 7th power minus 1,250. Okay, so this amount in here, this basically is what he made after, or all, not exactly what he made, because that's what he deposited plus interest. But after 7 years, they have $5,206.67. And then we have to subtract off the $1,250. So if you do that, this is $3,956.67. So technically, this is kind of like what he's investing in 2007 with the same deal he had before. And now he's investing, and we want to see how much he has in the account now, or and so we have to figure out how many years has it been since 2007, from 2007 to now. And so now we have T is equal to 13 years. So this is the amount invested. From 2007 to 2020. And so here, time is equal to 13. Okay. So let's plug this in. So we have our amount is equal to $3,956.67. 1 plus 0.048. And this is all raised to the 13th power. So it's 3,956.67, 1.048 raised to the 13th. And so this is given us amount is $7,278.24. Okay, so basically they had the amount in their account for 20 years, but they took out that 1,250 7 years into it. Okay, so let's look at one more, and then I want to get into some other things. Okay, so in 2003, the population of the state of New York was 10.78 million people. In 1990, it was 7.99 million. Using the population growth formula, y equals AE raised to the KT. Determine the value of K. New York's relative growth rate or rate of growth. Okay, so this is a little bit different than that growth rate formula we looked at before. E is just 2.718. E, that base maps a lot of stuff. It tends to follow a lot of real life situations. So we're given that y is equal to A times E raised to the KT. So A is equal to the initial population. T is time, and we're talking about in years. And K is equal to the growth rate. And P equals the population of New York after T years. T years since 1990. Okay, so we've been given a bit of information so that we could figure out what our K value is. Okay, so let's first look at the initial equation. Y, the population of New York, is equal to the initial amount. It tells me here in 1990, there was 7.9 million people. So I'm going to put 7.99 million people times E raised to the KT. Okay, this is similar to the other problem where we needed to figure out what one of the variables was, but it gave us enough information, basically a point, where we could figure out the other variable. So it tells me in 2003. So let's figure out T equals what in 2003? Well, this is T equals number of years since 1990. So in 2003, that's 13 years. We're given what the population is then, and so that is what Y is. We were given that in 2003, when T is 13, there's 10.78 million people. So let's go back in and plug in those values, and then we'll just have an equation with just K in it, and we can solve for it. So we have our Y value, which is 10.78 million people, is equal to our initial amount, which was that 7.99, E raised to the K times T, but T in our case is 13. Okay, so now we want to solve for K. So we need to isolate the exponential piece. So we don't want the coefficient, the number in front of that exponential piece. And so we can undo that by dividing both sides by 7.99. And so we have 10.78 divided by 7.99 is equal to e to the 13k, or k13. I'm not going to reduce that or put that in the calculator until the very end. So simplifying while you're working these out can make a big difference on the value of k or an effect. So don't simplify until the end. So let's take the natural log of both sides. I want to take natural log versus log because I have an e function, and I know natural log of e is just the exponent. And so taking the natural log of both sides of my equation, you have the natural log of this 10.79 or 78 all over 7.99 is equal to the natural log of e to the 13k. So we have the natural log of this piece, 10.78 all over 7.99 is equal to, so again, natural log of e, this is saying e to what power? What would I have to raise e by to get back e to the 13k, which is just 13k. So get k by itself, we can divide both sides by 13. So let's plug that in the calculator so I can get an approximate value of k now. So I have the natural log, parentheses, so 10.78 divided by 7.99. In that parentheses, divide that by 13. You get k is approximately 0.0230386. So if this information is right, this is the growth rate of the population. So this is about, move your decimal place over twice. So the growth rate is approximately 2.3% per year in New York. I would probably ask you what the equation was. So find the equation. That gives you the population. After t years. Okay, so we pretty much have it. We have y equals the initial amount. So y equals our 7.99. E raised to the k. Okay, so we have to put this in the decimal form though. So 0.0. Again, on these, I don't tend to round just because it kind of affects it. So that all times t. Okay, so if this was true information, I don't know if that was true about the population in those times or not. But if that was true information and New York continued to grow at that rate, then we could figure out what the population was at any time. So if we wanted to figure out what it was in 2050, we would have to figure out how many years since 1990 is 2050, which is 60 years, and we would plug in 60 in for t. We could figure out in what year the population of New York reached a certain level by plugging that in for y and solving for t. Okay, so that is applications on exponential growth and logarithms. We're basically using logarithms sometimes to help us solve for a variable that's in the exponent. So now we're going to look at some variation problems. And so setting these up, you just want to follow kind of the directions. And if you have direct variation, let's say you have y equals k times x. K is the constant. So it's something that never changes for the problem. You will get something that reads something like y varies directly with x. So if you hear that when you're reading through the problem, you're going to want to write y equals k times x. They're always going to give us information, enough information to figure out what k is in the problem. We'll look at that in a minute. They might phrase this, and it means the same thing, is that y is directly proportional to x. So y is directly proportional to x. If it's an inverse variation, when we write out our equation, the generic form is going to be y is equal to, we always in these variation problems have this k, at least that's what we call it, or I have been calling it all these years. So you have this y equals some constant k all over x. And here we would say, if we wanted to write that equation in the form, it would say y varies inversely with x. Or y is inversely proportional to x. Okay, so another type that you might hear is jointly. So joint variation. So y is equal to k times x times z. So in this case, we would say y varies jointly with x and z. Or varies jointly proportional with x and z. Okay, so those are just kind of key phrases on how we're going to set up these problems. So let's look at some examples. So if it said A is proportional to the square of t and inversely proportional to the cube of x. Okay, so in this example, all we're doing is write an equation that expresses the statement. So it says A is proportional. So I know that this is meaning A is equal to. We always have K in here. So A is equal to K. And so now it's going to tell us how we're going to do this. So it's proportional to the square of T. So proportional means multiplication in this case, and the square of T. So I can write T squared, T raised to the second power. Then it tells me though, it's inversely. That means I'm going to have it in the denominator. Proportional to the cube of x. Well, cube of x, it could be written as x cubed. And so now we wrote this statement with the information given. Okay, so in this example, we're going to express the statement as an equation, use the given information to find the constant of the proportionality. Okay, so we're going to find the equation. And our constant. Okay, and the proportionality. So maybe faster if I just type it. So let's look at the following. T is jointly proportional to x and y and inversely proportional to r. If x is equal to 2, y is equal to 3, r is equal to 12, then t is 25. That's a lowercase t. Okay. So first thing you want to do is you want to set up that generic equation just with the variables. And so reading through this, this is saying that t is jointly proportional. So that's telling me I'm having t equals. Again, I'm always having that constant k in here, so I always just put that k in there. And so now I'm going to read through to figure out what it is proportional to. So it's proportional to x and y jointly, so that means multiplication. So x times y. And then it says inversely proportional, so that means division, to r of r. Okay, so here's our general form of this equation that represents that information. So this is our equation. Now we can plug in our variables. X equals 2, y equals 3, r equals 12, and t equals 25, so that we can figure out what k is. So it's just substitution. So t is 25, so 25 is equal to, k is what we're looking for, so k times my x value, which is 2 up here, times my y value, which is 3, all over my r value, which is 12. Okay, so I notice I can simplify a little bit before I get k by itself, because I have division and this is strictly multiplication on top and a single term on the bottom. Well, 2 times 3 is 6. 6 goes into 12 twice. And so I'm really left with k times k over 2. So to get k by itself, we can clear the fraction by multiplying both sides by our denominator of 2. And so we get k is equal to 2 times 25, which is 50. So technically, we now have our equation. So t is equal to k, which is 50, jointly with, so times x and y, x times y, all inversely, so all over r. Okay, so again, key thing on here is to kind of nitpick it, set up the generic equation with all the variables. They're going to give us enough information that we can plug in numbers to figure out what that k constant is. And then usually they're going to ask us a question. So let's go to a word problem now. So I'm gonna start typing this word problem. So it says the cost, C, of printing a magazine is jointly proportional to the number of pages, P, in the magazine, and the number of magazine printed, M. Okay, so actually before I even type anything else, let's just set that generic form up. So it says the cost of a printing magazine is jointly proportional. And it tells me the variables to use. So it says the cost C, so C, if I ever see varies jointly, varies proportionally, whatever, I see those words, I put the equal. I always have the K in there, K times, and let's see what it tells us. So the cost of printing the magazine is jointly proportional, so I have some multiplication, to the number of pages, P. So I know that is jointly, it's multiplication here, in the magazine, and the number of magazines printed. M, so times M. Okay, so now we have the generic equation, and so they're going to throw information at us so that we could figure out what K is and then answer anything else. So part A, and I might have already done part A, write an equation that expresses this joint variation. Yeah, we did it. Part B, find the constant of proportionality if the printing cost is $60,000 for 4,000 copies of a 120-page magazine. Okay, so basically it gave us, like I told you, it's going to give us enough information to find K. And so it's going to give us what our variables are. It tells us what the cost is. Cost is $60,000. So we have our generic equation here, which is C. So C is 60,000. So 60,000 equals, K is what we're trying to find. So write K times the number of pages. So P was number of pages. It has 4,000 copies and a 120-page magazine. So P in our case is equal to 120. So K times 120 times the number of magazines. So the number of magazines, M, was 4,000. Okay, so before I plug things in the calculator, I'm just going to divide both sides by 120 times 4,000, just because I see that things are going to cancel kind of nicely when I do that. So I get K is equal to my 60,000 divided by what was on the other side, which was the 120 times 4,000. So I need things start canceling with my zeros, first of all. So 1, 2, 3, 4. I have 4 zeros there, and I technically end with 4 zeros with that 120 there. So basically, I could divide the top and the bottom by 10,000. They both have that in common. And then I notice, basically, I'm left with 6 in my numerator, all over 12 times 4. Well, 6 goes into 12 2 times and itself once. And so without even a calculator, I get that K is equal to 1 over 2 times 4, which is 1/8. So now we can answer anything they give to us. We now actually have this equation, and we know what that constant K is, and that K for this problem never changes. So the cost of this magazine, well, that's not necessarily true. For now, things might change in the world where costs are different. So the cost for this magazine is 1/8 times the number of pages, P, times the number of magazines, M. Okay, so now that we can answer any thing they throw at us with that equation. And so they want to know now, part C, how much would the printing cost be for 5,000 copies of a 92-page magazine? Okay, so we know how many pages there are and we know how many magazines. We're looking for cost. There's 5,000 copies, so that's M, and it's a 92-page magazine, which is P. And we're looking at how much our cost is going to be. So C is equal to my K value, which is 1/8, times number of pages, 92, times number of copies, 5,000. So I can start reducing. Or 92 times 5,000, all divided by 8. So the cost for producing that many magazines of 92 pages is going to be $57,500. Let me give you another example. Okay, this looks interesting. The power P, parentheses, measured in horsepower, HP, end of parentheses, needed to propel a boat is directly proportional to the cube of the speed s. Write an equation that expresses this variation. Okay, so the power P needed to propel a boat is directly proportional. So I know P is equal to proportional to the cube, and so I need my K there. K times the cube of the speed s. So that would be s cubed. So there's our equation. Part B. Find the constant of proportionality for a boat that needs an 80 horsepower engine to propel the boat at 10 knots. Okay. So find the constant. We need to find K. And so We're looking for K, and they're going to give us enough information to put in. So for a boat that needs an 80 horsepower engine to propel a boat at 10 knots. So 10 knots is our speed, 80 is our power. Um, 10 knots. So we're going to have 10 and then cubed. So now we can figure out what K is. We have 80 is equal to K times 10 cubed. 10 times 10 times 10 is 1,000. So we can divide both sides by 1,000 to get K by itself. So 80 over 1,000, well, 10 goes at least into both of them. I know 4 goes into both of them. 4 goes in there twice. They're 250. So I get my K value is equal to 250. So basically now I have the equation for a horsepower boat that has 80 horsepower. Let's see, and 10 knots. So P is equal to 250 times our speed, S cubed. And so now we can answer anything they throw at us. So C. How much power is needed to drive this boat at 15 knots? Okay, so we're trying to find the power, P. And we know what our speed is, S. So this is equal to K, which is 250, all times S, which is 15 cubed. So 15 cubed is 3,375. So we have 250 times 3,375. That seems like a lot of power. Okay, I know what I did wrong. That 2 over 250, that was 2 over 250, not just 250. And that actually reduces a little bit too. Sorry about that. Two goes into both of those, right? 2 goes into itself once. 2 goes into 250, 125 times. This is 1 over 125, or 2 over 250. Okay, so here's a case where understanding what you're doing and the numbers helps you to see if you did something wrong or wrote something wrong. Okay, so let's go back. So 3,375 divided by 125. This is equal to 27. Okay. That doesn't make sense either, does it? How much power is needed to drive this boat at 15 knots? When it was driven at 10 knots, our horsepower was 80. If we're going 15 knots, that means I am going faster. And my guess is I'm going to need more horsepower, right? And it's telling me my horsepower, if I just did this right, is 27. Sorry, I keep pushing something along. So that's where I got to go back and kind of look at my work and see if I can find it. So I'm going to pause this while I look. Okay, so yes, we found, thank you. It's helpful to have other eyes. 8 over 100 is reduced to 1 over, sorry, 4 goes into that twice, right?
It's the 80 over 1,000 ends up being 225, and
Right, 2 over 25. I guess we can leave, that doesn't really reduce.
it doesn't, unless you want to do it into decimals.
And it wouldn't matter if that was a clean decimal, which it probably is, which is 0.08.
Uh-huh.
Okay, so either way, you can plug it in there. So 0.08. Okay, so one more time, 3,375 times 0.08 is 270. So we need 270 horsepower to get up to 15 knots. Where you only need 80 to get up to 10 knots. To me, it seems like a lot. I don't think I'm in a book that has the even answers. Okay. I am in a book with the even answers. Let me just check. Okay, so we did it. We got it right. So I think what I'm going to do is let's do one more problem of variation. Tuesday or Monday, we will meet again, and we will go over circles, which will be, I think, good kind of helpful review to help you remember how to complete the square. And we'll review also on Monday. And then the exam is on Wednesday, and then the final is the following, I believe, Wednesday. But I'll post that on Canvas. Okay, so let's look at an example where they don't lay it out for us like it just did, where it kind of broke it up saying, okay, find the general equation, now find K, now figure out this information. So this is a problem where it's just kind of all of it is together. It doesn't have parts, but same sort of idea. Value of a lot, that kind of sounds cool. The value of a building lot on Galliano, and I don't know if I'm pronouncing that right, island is jointly proportional to its area and the quantity of water produced by a well on the property. A 200-foot by 300-foot lot has a well producing 10 gallons of water per minute. And is valued at $48,000. What is the value of a 400-foot by 400-foot lot if the well on the lot produces 4 gallons of water per minute? Okay, so we need to start, it doesn't give us the variables. We want to set up variables. So a variable, so a value of a building on this island is jointly proportional. So maybe for building, or V for value, is equal to, we always need K times. So jointly proportional. So that means it's multiplication to its area. So area. So let's put A here for area. And the quantity of water produced by the well. Maybe W. For water produced by the well. Let's go back and clean this up because it looks like they're giving us the area. They're giving us the length and the width. And so I guess we don't have to. Okay, so that's what our generic equation is. And now we can figure out what K is. So they're giving us enough information to figure out what K is. And so it tells me that a 200 by 300-foot lot. Okay, so the area of this 200 by 300-foot lot is 200 times 300, which is equal to 2 times 3, which is 6, and we have 4 zeros. So 60,000 square feet lot. So let's put that in. We have K in there, times A, which is 60,000. Times our well. Our well is producing how much water? 10 gallons per minute. So times 10. And we're given the price of the lot. What is the value is The V value is 48,000. So we have enough information here now to figure out what K is. So if we take that 48,000 and we divide both sides, well, 60,000 times 10, so that's really 600,000. So dividing by 600,000. I cancel out the same number of zeros. 6, I know at least goes into both of those. 6 goes into 48 8 times. 6 goes into 600 100 times. Well, 4 goes into both of those. 4 goes into 8 twice. 4 goes into 125 times. That one looks familiar, doesn't it? 2 divided by 25, which was, I believe, that 0.08. So 0.08. Okay, so now we actually have the value of a lot in this, on this island, depending on what the area of that lot is and what the well water rate is. And so we're going to use this formula to answer what they ask. So we want the value of a 400 foot by 400 foot lot. Okay, so A in this case is 400 foot by 400 foot. Which is 160 square feet, 160,000 square feet. So I got the value is equal to my 0.08 times my area, which is 160,000 square feet, times the water rate. And our water rate is just 4 gallons per minute. So times 4. Okay, so 0.08 times 160,000 times 4. So this gives us back, the value of that lot would be $51,200. Okay, so again, some of these can seem overwhelming at first when you're just thrown with all that information, but with word problems, just read through them, then go read through them again and kind of just nitpick it. And with these variation problems, they're all basically the same. They're going to give you some generic formula. We know we always have K there, and it just has to do with the wording. Is it jointly, directly, proportionally? That's all multiplication. Inversely is division. They're going to give you enough information for all the variables but K so that you can figure out what K is. You're going to plug that back into your generic formula and then you can answer anything. They're going to give you all the numbers but one variable so you can solve. So hopefully that wasn't too bad and you don't have problems when you go through the homework.